Everybody loves to tell you that electricity is like water flowing through a pipe, voltage is like pressure, current is like the flow rate, resistance is like sand in the pipe. It's a beautiful analogy. It's simple. It's easy to picture in your mind. And it's wrong. Well, not completely wrong, but wrong enough that if you keep using it, you're going to get yourself into terrible trouble. Now, I'm not saying the people who teach you this are bad people. They're trying to help. They're trying to give you something familiar to hold on to. But here's the problem. When you make an analogy, you're saying, this thing I don't understand is like this thing I do understand. But what happens when the thing you're trying to understand is fundamentally, profoundly different from the thing you're comparing it to? What happens is you start believing things that aren't true. Let me tell you what I mean. When water flows through a pipe, what's actually happening? You've got molecules, billions and billions of them, bumping into each other, pushing each other along. The water at the front pushes out. The water at the back rushes in to fill the space. It's mechanical. It's local. One molecule pushes the next one. That's how water works. But electricity? Electricity is nothing like that. Nothing at all. When you flip a light switch, you think the electrons are racing from the switch to the bulb like water racing through a pipe. But that's not what happens. The electrons in the wire are already there, sitting in the copper atoms. When you close the circuit, they start to drift. And I mean drift. They move about 1 millimeter per second. 1 millimeter! If electricity really worked like water, you'd flip the switch and wait about an hour for the light to come on. So what's actually happening? What turns the light on instantly? It's the field, the electromagnetic field. The moment you close that switch, the field changes everywhere along the wire at very nearly the speed of light. And it's this field that pushes on all the electrons at once, all along the wire, simultaneously. The electrons don't have to travel from the switch to the bulb. They're already at the bulb. The field just tells them to start moving. You see, this is where the water analogy completely breaks down. Water is stuff. It's matter. It flows from one place to another. But electricity isn't about stuff flowing. It's about fields. And fields are not stuff at all. A field is a condition of space. At every point in space, there's a number or a direction that tells you what would happen if you put a charge there. That's what an electric field is. And here's the thing about fields that makes them so different from water. They can reach out across empty space. You can have an electric field in a vacuum where there's no matter at all. Try making water flow through empty space. It doesn't work. Water needs something to be. The field doesn't need anything. It just is. Now let me tell you about something even stranger. When you have a current flowing through a wire, it makes a magnetic field. The magnetic field circles around the wire. This is something that has no analogy with water whatsoever. If you've got water flowing through a pipe, does it make a magnetic field? No. Does it make anything circling around the pipe? No. It just flows. But electricity creates this whole other field perpendicular to the current, wrapping around it in circles. This was discovered by a fellow named Ørsted in 1820, and it shocked everybody because nobody expected it. And then there's the reverse. If you take a magnet and move it near a wire, you create an electric field in the wire. The magnetic field, when it changes, makes an electric field. This is called electromagnetic induction. Faraday discovered it. And this is how generators work. You spin a magnet, the magnetic field changes, and it creates an electric field that pushes electrons around. Try doing that with water. Move some water near a pipe and see if it makes water flow in the pipe. It doesn't happen. There's no analogy. Water and magnetism have nothing to do with each other, but electricity and magnetism are intimately connected. They're really two aspects of the same thing, the electromagnetic field. In fact, whether you see an electric field or a magnetic field depends on how you're moving. If you're sitting still and you see a charged particle sitting still, you say there's an electric field. But if you're moving past it or it's moving past you, suddenly there's also a magnetic field. They're mixed together by motion. They're unified. Maxwell figured this out. He wrote down 4 equations that describe everything about electricity and magnetism. And when he put them together, he discovered something absolutely remarkable. These equations predicted that electromagnetic disturbances would travel through space as waves at a particular speed. And when he calculated that speed, it came out to be 300 million meters per second, the speed of light. That's when he realized light is an electromagnetic wave. It's electricity and magnetism combined, propagating through space. Now tell me, what does that have to do with water flowing through a pipe? Nothing. Absolutely nothing. Light is electricity. Radio waves are electricity. X-rays are electricity. They're all the same thing, just oscillating at different frequencies. The whole electromagnetic spectrum, from radio to gamma rays, it's all explained by these same equations, Maxwell's equations. And here's another place where the analogy fails completely. Capacitors. You know what a capacitor is? It's two metal plates with a gap between them, no connection. You charge one plate up positive, the other negative, and you've stored energy. Now, how do you explain that with water? You can't. There's no gap in a water pipe that stores water. If you put a gap in a water pipe, the water just stops. It doesn't flow anymore. But in a capacitor, when you're charging it, current flows in the wires leading to it, even though there's a gap. How is that possible? It's because the changing electric field between the plates is equivalent to a current. Maxwell called it the displacement current. The field changes, and that changing field continues the current. This was Maxwell's great insight, the piece that completed the equations. Without it, electromagnetic waves wouldn't exist. Without it, you couldn't have radio, television, cell phones, Wi-Fi, none of it. Does water have a displacement current? Can you have water flowing even though there's a gap in the pipe? Only if you're willing to accept magic. But in electricity, it's not magic. It's the field. Let me tell you about another problem. AC current, alternating current. The current goes forward, then backward, then forward again, 60 times a second. Now, if electricity were really like water sloshing back and forth in a pipe, the electrons would just wiggle back and forth a tiny bit, and that would be it. But that's not what happens. What happens is that the electromagnetic field propagates outward as a wave. The energy travels. It travels at the speed of light, or close to it, depending on the medium. The electrons barely move at all, but the energy goes racing away. This is how a radio transmitter works. You make electrons oscillate back and forth in an antenna. They wiggle. But the electromagnetic field that they create doesn't just wiggle. It detaches and propagates outward as a radio wave. That wave can travel across the world. It can travel across the solar system. Voyager 1 is out past the edge of the solar system right now, and we're still receiving its radio signals. Those are electromagnetic waves that have traveled for billions of miles through empty space. Try doing that with water. Here's another thing the water analogy gets wrong. Superconductivity. When you cool certain materials down to very low temperatures, their electrical resistance drops to exactly zero. Not almost zero, exactly zero. You can start a current flowing in a loop of superconducting wire, and it will flow forever, literally forever. As long as you keep it cold, that current will never stop. There's no friction, no resistance, nothing. Can water do that? Can you make water flow through a pipe with no friction? No. Water always has viscosity. There's always friction. The water analogy says resistance is like friction in a pipe, but then we discover that resistance can completely vanish. The analogy breaks. It doesn't work anymore. And let me tell you about quantum mechanics, because that's where things get really strange. An electron is not a little ball. It's not a tiny sphere of charge rolling along like a marble. An electron is a quantum object. It has wave properties. It has particle properties. It exists in a kind of cloud of probability until you measure it. The whole notion of an electron as a thing moving along a path like a water molecule in a pipe is wrong. When you start to describe electricity at the quantum level, you have to talk about photons. The electromagnetic field is quantized. It comes in discrete packets of energy called photons, and these photons are what actually carry the electromagnetic force. When two charged particles interact, they exchange photons. Virtual photons, we call them, because they pop in and out of existence too quickly to be directly observed. But they're there. They're real. That's how the force works. Does water exchange virtual water molecules to create a force? Of course not. That's absurd. The analogy has completely collapsed. Now, I know what you're thinking. You're thinking, okay, fine, the water analogy isn't perfect, but it's still useful for beginners. And maybe that's true. Maybe it helps people get started. But here's my concern. Once you learn to think of electricity as water, it's very hard to unlearn it. It gets stuck in your mind. And then when you encounter something that doesn't fit the analogy, you get confused. You think electricity is misbehaving, but electricity isn't misbehaving. It's doing exactly what it should do. It's just not doing what water would do. I think it's better to teach what's actually happening, even if it's harder. Tell people about fields. Tell them that space itself can have properties, that there can be something at every point in space that affects charges. Tell them that electricity and magnetism are unified. Tell them that light is an electromagnetic wave. These things are true. These things are beautiful. And they're not actually that hard to understand if you approach them directly instead of through a broken analogy. You see, the real trouble with the water analogy is that it makes electricity seem less interesting than it actually is. It makes it seem like just another kind of flow, like traffic on a highway or blood in your veins. But electricity isn't just another kind of flow. Electricity is fundamental. It's one of the four fundamental forces of nature. It holds atoms together. It makes chemistry possible. It makes biology possible. Without electromagnetism, there would be no stars, no planets, no life, no us. And the theory that describes it, Maxwell's equations combined with quantum electrodynamics, is one of the most beautiful and successful theories in all of physics. It's been tested to incredible precision. Every prediction it makes has been confirmed. It explains an enormous range of phenomena, from the smallest scales to the largest, and it has nothing to do with water flowing through pipes. So here's what I want you to do. Forget the water. Forget the pipes. Forget the pressure and the flow. Start fresh. Think about fields. Think about how a field at one point can affect what happens at another point. Think about how changing electric fields make magnetic fields, and changing magnetic fields make electric fields, and how these two fields can dance together in a wave that carries energy through space. Think about how every electron in a wire knows instantly when you close a switch, because the field tells them all at once. Think about how this same field can travel across empty space and carry information from one side of the universe to the other. Think about how the light you see is made of the same stuff as the radio waves that bring music to your car and the X-rays that let doctors see your bones. That's electricity. That's electromagnetism. And it's so much more beautiful, so much more interesting, so much more profound than water in a pipe could ever be. Now, does this mean the water analogy is useless? Not entirely. If you understand the limitations, if you know exactly where it breaks down and why, then sure, use it for a quick intuitive picture of Ohm's law or something simple like that. But don't let it become your mental model for what electricity really is, because it isn't. The universe doesn't run on analogies. It runs on laws, real laws, mathematical laws. And those laws tell us that electricity is fundamentally about fields pervading space, not stuff flowing through tubes. Once you grasp that, once you really understand what an electromagnetic field is and how it behaves, everything else starts to make sense. Circuits make sense. Antennas make sense. Motors and generators make sense. Light makes sense. And you know what? It's not even that hard. People think fields are abstract and difficult, but they're not. You just have to think about them directly. Don't try to translate them into water. Don't try to make them into something familiar. Let them be what they are. Let the universe show you how it actually works instead of how you wish it worked. That's what physics is about. It's not about making things simple. It's about making things true. And the truth about electricity is far stranger and far more wonderful than any analogy could ever capture. So stop imagining electricity like water. Start imagining it like what it is: a field, a wave, a quantum phenomenon, a fundamental force of nature. Start seeing it as part of the unified fabric of electromagnetism that holds the universe together and makes everything you see and touch and experience possible. That's the real truth about electricity, and it's a truth worth knowing.